Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello everyone and welcome to this next lecture in the Build DeepSeek from Scratch series. Today we are going to learn about grouped query attention. In the previous lecture we started learning about techniques which we can use to solve the KV cache memory problem. And the first technique which we learnt about was the multi-query attention. And today we are going to learn about the grouped query attention. First, let me do a quick revision of what we learned in the multi-query attention. Essentially, it all started by looking at the KV cache. So during inference, we cache the keys, we cache the keys matrix, and we cache the values matrix during the inference time. And as a result, we don't have to do repeated calculations again and again while predicting the next token. That's the main idea of the key value cache. Although the key value cache offers a lot of benefits, such as it offers a linear relationship between the input tokens and the compute time, whereas if you don't do caching, then the compute requirements rather, then the amount of computations which we need to do increase quadratically if we don't do caching. If we do caching, on the other hand, the amount of computations needed increase linearly with the input tokens. So we save on a huge amount of computational cost, and we don't have to do repeated computations again and again. That's one main benefit of the KV cache. However, it comes with this dark side which we learnt about in the previous lectures, and that dark side is that it takes a lot of space in the memory. In fact, the memory requirements of the KV cache, or the size of the KV cache, grows with the number of transformer blocks, the batch size, the number of attention heads, the attention head size, and the context length. As all of these parameters increase, the size of the KV cache grows. So, for example, for GPT-2, it's a relatively small model. The KV cache is just 36 MB. But for GPT-3, the KV cache grows to 4.5 gigabytes. If we go to even bigger models like the DeepSeek R1 or V3, for example, this model uses 61 transformer blocks. Even if we assume a batch size of 1 during inference, the number of attention heads is 128 and the attention head dimension is also 128, along with a context size of 100,000. With all of these parameters, the KV cache size for the DeepSeek model becomes as huge as 400 GB. Now, if we take up this much space in memory, it slows down our computations and we also have to pay more. So imagine a company has built a foundational model with just the normal variant of this KV cache. The company has to pay a lot because it has to store a lot of parameters during the inference time. And naturally, this increases the cost which the company charges to the clients for inference. But as we know, DeepSeek inference cost per API call is very low. It's incredibly less. So clearly, it's not using this normal variant of the KV cache, right? So people have figured out ways to solve the KV cache memory problem. And the ultimate way is the new innovation which DeepSeek implemented, and that's the multi-head latent attention. But to get to that, there were two other innovations. The first one was the multi-query attention, which we learned about in the previous lecture. And today we are going to learn about group query attention. The key concept of multi-query attention is very simple. What we learned in the previous lecture was that if in normal multi-head attention, when we look at the trainable keys matrix and when we look at the trainable value matrix, every head essentially has different values, right? So if you look at head 1 or attention head 2 or attention head 3 or attention head 4, these values are different from each other. That's why the color coding which I've used here denotes that every attention head has different values for WK, and every attention head similarly has different values for WV as well. Now, naturally, since the input embedding is multiplied with WK and WV to give me the keys matrix and the query keys matrix and the value matrix, when we look at the keys matrix K, the attention head 1 values are very different from the attention head 2 values, which are different from the attention head 3, and which are different from the attention head 4. And that's similar to the values also, to the values matrix. The values or the elements for each attention head are different from each other. Now, since these values for the keys matrix and the value matrix are different from each other for different heads, we have to store all of them in the cache. So we are caching the keys and the values, right? So when we cache the first head, we also have to cache the second head. We also have to cache the third head, and we also have to cache the fourth head. Similarly, for the values, we have to cache all the heads separately. And as a result, if you look at the formula for the KV cache size, you will see that it actually grows with the number of attention heads. The more the number of attention heads, the more the parameters we need to store. So in multi-query attention, people did a simple trick. They said that what if in the WK and in the WV matrix, I'll first take a look at the parameters in my attention head 1, and then I duplicate these same parameters for head number 2, head number 3, and head number 4. Similarly, for the values, I take my head 1 parameters and I duplicate it for head 2, head 3, and head 4. Naturally, what this will also mean is that in my keys matrix K and my value matrix V, my attention head 1 values, attention head 2, attention head 3, and attention head 4 values will all be identical to each other. There will be no difference in the values of the keys among different heads. Head 1, head 2, head 3, and head 4 will be the same. Now, if we look at the values matrix also, what we have for V1 will be the same for V2, for V3, and V4. So, in multi-query attention, keys and the value matrices have attention heads, and each attention head contains the same information, in fact the exact same parameters. So you can think of taking k1 and duplicating it to form k2, k3, and k4. You can think of taking v1 and duplicating it to have v1, v2, and v4, v1, v2, v3, and v4. Naturally, the consequence of this is that now, since the values for all the heads are the same, we just need to cache or store one of these heads. We don't have to store the matrices for all the different heads because these values are literally the same, right? So we can get rid of this factor n, the number of attention heads in the size of the KV cache. So when we use multi-query attention, um, let's say DeepSeek has 128 attention heads. When we use multi-query attention, we reduce the KV cache size by a factor of 128 from 400 GB to just 3 GB. However, although we save the amount of memory storage required by the KV cache, there are a number of disadvantages of the multi-query attention. And the major disadvantage is that it leads to significant performance degradation. The main reason for this performance degradation is that the intuition for multi-head attention was that the reason we introduced multi-head attention is that, let's say if you have a sentence like this: the artist painted the portrait of a woman with a brush. It can either be something like this, which is artist painting the woman with a brush, or it can be something like this, where the artist painted the portrait of a woman who had a brush in her hand. There can be two perspectives, right? Similarly, there are many paragraphs, sentences, text which have multiple perspectives. The reason we introduced multi-head attention was that we wanted every attention head to capture different perspectives, so that in the final context matrix we have perspectives from different attention heads. Now think about this fact that if the k1 and k2 values are completely similar to each other, if all the keys values across the heads are the same, the values are the same across the heads, that means that the diversity which we get across different attention heads is not that much. It's very low. What do I mean by diversity? I mean that the attention weights matrix for my heads and the context vector matrix for my heads, ideally they need to capture a lot more diversity, so they need to be different from each other by a lot of magnitude. But now we don't allow them to be as different from each other. Of course, the query vectors are different from each other. Q1 and Q2 are different, because in multi-query attention, we don't force Q1 to be equal to Q2. We just force K1 to be equal to K2, V1 to be equal to V2. So Q1 and Q2 are different. So the attention scores matrix across different heads will be different, but it won't be that different because K1, K2, V1, V2 are the same. So we are restricting the diversity captured by the different attention heads, and that leads to significant performance degradation in the case of multi-query attention. And that's where grouped query attention comes into the picture. Groups query attention is somewhere between multi-query attention and multi-head attention. So in multi-head attention, all the keys and the values had different key and value matrices have different values. In multi-query attention, all the key and the value matrices across different heads have the same values. Grouped query attention lies somewhere in the middle. Essentially, what group query attention says is that instead of all the attention heads having the same key value matrices, what if we create groups of attention heads? And what if those groups have the same values? Let me explain what this means in a lot more detail now. So here's the schematic of the multi-query attention. You see, based on the color codes here, head 1, head 2, head 3, head 4 have the same values for keys, and head 1, head 2, head 3, head 4 have the same values for the values matrix. In grouped query attention, what is essentially done is that we create groups. So here you see, this is group number 1. In group number 1, there is head 1 and head 2. Both of these will have the same values for WK. In group number 2, there is head 3 and head 4. Both of these will have the same values. Similarly, for the values matrix, group number 1 has the same values and group number 2 has the same values. This for WK and WV. Similarly, in the keys matrix K, what happens is that group 1 has two attention heads. Both these attention heads will have the same value, and group number 2 has two attention heads, and both of these attention heads will have the exact same values. Similarly, for the values matrix, group number 1 has V1 and V2, they will have the exact same values, and group number 2 has V3 and V4, they will have the exact same values. So you see what we are doing here. We are not saying that all attention heads will have the same values. Here all the colors were the same, right? So here all the colors were the same, and that's why there was not too much diversity which we obtained in the attention scores. But now you see what's happening is that the colors are not all the same. In multi-head attention, that's the best thing, because in multi-head attention, if you see, there was a complete diversity in the colors. Everything was different from each other. All these colors were different from each other, right? And in multi-query attention, nothing was different from each other. In grouped query attention, it lies somewhere between multi-query attention and multi-head attention, because now groups have the same colors. So overall, if you see, I am still not doing as good as the multi-head attention, because in multi-head attention, Every head has different content. But here what I'm saying is that, okay, I don't want to be as bad as multi-query attention, and I don't want to be as good as multi-head attention. Let me lie somewhere in the middle, which means that if there are 32 attention heads, and if I create 8 groups, let me write it here. If there are 32 attention heads, 6, 7, 8, whatever, there are 32 attention heads like this. Then let's say I create 8 groups. The first group G1, second group G2, third group G3, etc. Now in each group I will share the same key value content. But across these groups it will be different. So G1 values will be different from G2, will be different from G3, etc. I hope you have understood how group query attention lies somewhere in between multi-query attention and multi-head attention. Now, the reason grouped query attention was introduced is that it solves the drawback, slightly solves the drawback of multi-query attention. Here, what we did was the K1, K2, K3, K4, etc. The values were the same across all the heads. But now in group query attention, we are saying that look, we won't have it same across all the heads, like this example which we considered, right? Uh, this example of 32 heads which we considered, we won't have it same across all the heads, but I'll create groups. So although it won't be as diverse as multi-head attention, but I still have different groups. So I still have 8 different, in this case there are 8 groups, right? So I still have 8 different values in keys and the values matrices. So I can still capture more diversity across different heads. Maybe one head, if one head lies in group 1 and one head lies in group 2, they both have completely different values. So they will capture different perspectives. If one head lies in group 1, one head lies in group 8, they will capture completely different perspectives. So again, let's take an example, and let's say I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Let's say I have 16 attention heads, and let us visualize, um, and I will draw all three now. And let us now visualize multi-head attention, multi-query attention, and grouped query attention. Okay. So in multi-head attention, let's start with multi-head attention. In multi-head attention, so let's say this is head 1, head 2, and this is head number 16 for all. In multi-head attention, all these heads will have different keys and values. There won't be anything common. In multi-query attention, all these heads, head 1, head 2, head 3, will have the same values. But in grouped query attention, we'll create groups. This group will have one value, this group will have another value, etc. So let's say if I take head number 3 and if I take head number 6, if I take head number 3 and if I take head number 6, in multi-query attention, head number 3 and head number 6 will have the same key value content. So these heads won't capture that much diversity in the text or in the information which is given, because they have the same key values. Although their queries are different, but we are restricting them by having the same key values. But now if I consider H3, this is H3, right? And this is H6. H3 and H6, they both have different key values because they belong to different groups. So they will capture more diversity. But in so this is H3 and H6 where we clearly prove that GQA is better than MQA. But now let us consider H1 and H2. If you consider H1 and H2, head 1 and head 2, uh, if you consider head 1 and head number 2, in GQA, they both belong to the same group. So they will contain duplicate key values. They will contain the key value matrices for head 1 will be the same as the key value matrices for head 2. In multi-query attention, anyway, everything is the same. So the key value matrices for head 1 and head 2 are the same. So there is no difference between MQA and GQA. And MHA is still better because H1 and H2 will have different values. So that way you can see that for some group, for some heads, GQA is better than MQA. For some heads, it's the same as MQA. That's why GQA lies somewhere in the middle. So MHA is the best in terms of diversity. Then comes GQA and then comes MQA. This only in terms of diversity. In terms of Memory of the KV cache, it goes in the other way, which we'll come to right now. So now let us calculate the KV cache size for all three of them, right? For multi-head attention, the KV cache size depends on n, which is the number of attention heads. In multi-query attention, this n was not there. So there was a reduction by 1 by n because all the heads carry the same key value. In grouped query attention, this n is now replaced with the number of groups which I have, right? So for example, let's say I take this case, what do I need to cache? I need to actually cache only one one matrix from group 1, and I need to cache one matrix from group 2. That's it in the keys. For the values, I need to cache one matrix from group 1 and I need to cache one matrix from group 2. So essentially, based on the number of groups which I have, I need to cache those many matrices. If I have 10 groups, I cache 10 matrices, one from each group. So this n factor here is now replaced with G. So let's say in DeepSeek, this n was 128. And if the number of groups are 8, this is now replaced with 8. So there is still the KV cache reduction which we obtain, 128 by 8. In the multi-query attention, the KV cache reduction was the maximum because it was 128 by 1, which is 128 times. In the case of grouped query attention, the reduction would be 16 times. 128 divided by 8, which is 16. So GQA has better performance than MQA. So this is in terms of diversity. In diversity, when I mean diversity, I mean the different perspectives which my attention heads can capture, making my language model better. GQA is better than MQA, but it's still not as good as MHA. We are still doing a bit of cheating. We are not doing as much cheating as we did in multi-query attention, but still slight amount of cheating is being done. Um, so if you actually compare multi-head attention versus multi-query attention versus group query attention, you'll have to compare along two verticals. First is the KV cache size and one is the performance. In the KV cache size, multi-head attention is the largest because it takes all the attention heads. Multi-query attention is the smallest because there is a division factor of 1 by n. And group query attention lies somewhere in the middle. It's still lesser than multi-head attention, but it's higher than multi-query attention. So the factor here is actually G by n, where G is the number of groups. That's for the KV cache size. For the performance, which is context understanding, multi-head attention performs the best because every head has different values of key and value matrices, so it captures more diversity, more perspectives. Multi-query attention is the worst. The reason it's the worst is because it's because every head has the same value, and you'll see that grouped query attention lies somewhere in the middle again. It lies somewhere in the middle because it's better than multi-query attention, but it's not good as multi-head attention in terms of performance or context understanding. So you see, grouped query attention lies somewhere in the middle. It's in terms of KV cache size is in the middle between MHA and MQA. In terms of performance also, it's in the middle between MHA and MQA. So that's about group query attention. Once you have understood multi-query attention, group query attention is just a small extension where we create groups. Now what I've done is that I've created a small code which we are going to go through, where we are going to take a very well-known model which uses group query attention. And that model is Llama 3 8 billion. So if you see Llama 3 8 billion and if you search group query, you will see that Meta themselves have had mentioned when the Llama 3 was launched on April 18, 2024. They themselves have mentioned that they have adopted grouped query attention across both the 8 billion and 70 billion sizes. So when I was constructing a tutorial for this topic, I was going through models which I can use to explore. Naturally, I came across Llama 3. So then I wanted to explore further with Llama 3, and I wanted to actually create a heat map across the different heads so that I can visualize the groups which are there. And I wanted to see whether the keys across groups are the same and the values across groups are the same. So that's what I did actually exactly. Here is my Hugging Face key, which should not be exposed, but you can create you can log into Hugging Face, and to access this model through Hugging Face, you will need to submit the access request actually. So you can click on this, and I have access to this right now. But if you don't have access, you will need to submit your details, and only then you can get access. Once you get access, in 1 to 2 hours, you will get access, and a notice will come that you have been granted access to this model, and then you can start using it. So they require your details, but I guess it's fine. At least they made the full thing open source. So then what I do is that I download this model from Hugging Face. That's the first thing which I do, and it does not take too much time. Although I ran it on an A100 on a T4 GPU, also this will run. I ran it, I downloaded it through Hugging Face, and then what I did is that I wanted to visualize. So first, let's look at the keys only. Let's look at the keys. Let's worry about the values later. What I wanted to do was that I wanted to create some sort of a visual like this. I wanted to look at group number one. I wanted to look at group number two, group number three, etc. So I had read somewhere that this model actually has 8 groups. This model has 8 groups, and each group has 4 heads. So there are 32 total attention heads, and each group has 4 heads. So group 1 has 4 attention heads, group 2 has 4 attention heads, etc. What I wanted to do was that I wanted to visualize. I wanted to visualize the query. I wanted to visualize the keys. I wanted to visualize the keys matrix, and I wanted to visualize the values matrix. So this I wanted to visualize the keys matrix for every group. So now there will be K1, K2, K3, and K4, the keys matrix for group 1. Then for group number 2, there will be K5, K6, K7, and K8, etc. Like that. And what would be the dimensions of the keys matrix? The dimensions of the keys matrix will be based on the input tokens which I have, and the head dimension essentially. So I'm looking at, so if you look at this, the number of rows will be the number of input tokens, and the number of columns would be the dimension for that particular head. So I just want to visualize. Ideally, K1 should be equal to K2, should be equal to K3, should be equal to K4, because within one group, all the key matrices will be the same. But for the second group, the key matrices should be different from each other. That is what I wanted to visualize. And then I just wrote a simple code for this, where I took the keys matrix, and then I just constructed a heat map. So, for example, if you see, every row corresponds to a particular group. The first row corresponds to group number 0. So here the indexing is from 0. Group 1, then group 2, and right up till group number 7. So if you look within one particular group, if you look at group number 0, you'll see that for head 1, head 2, head 3, and head 4, we have the same values. So look at this, and this. It's the same content, because within one group, all the matrices have to be the same. If you look at the second group, within that second group, you'll see that all the matrices are the same. Similarly, if you go right till the very end, and if you look at the last group, you'll see that all the matrices visually are exactly the same. This is proof that Meta Llama 3 used a group query architecture. And now if you compare group 0 and group 1, it's different. Group 1 and group 2, it's completely different. Group 2 and group 3, it's completely different. So within one group, it's the same. The key value, the key matrices are all the same, but across different groups, they are different. That's the advantage of GQA in terms of MQA, especially in terms of the diversity which we discussed, capturing more context, doing well with respect to understanding perspectives, etc. So I hope this visual makes it clear to you that Llama 38 billion uses a grouped query attention, because in each group you will see that the key matrices are exactly the same. Then what I did is I did the same thing for the values. I did the same visualization for the values, where for the values also, within let's say group number 1, v1 should be equal to v3, should be equal to v1, v2, v3, and v4. Then in group number 2, v5 should be equal to v6, should be equal to v7, should be equal to v8. This is exactly what I tested next. So my next plot was exactly replicating this, but now I did it for the values. So if you see, group 0 has the same values matrix. across all my heads: head 1, head 2, head 3, and head 4. Group number, the next group has the same values matrix across all the heads. Similarly, if you go right down till the very end, the last group has the same value matrix across all the heads. But now if you compare between the first group and the second group, the value matrices differ. From the second group and the third group, the value matrices differ. So group 1 has different value matrices than group 2, dot dot dot, right up till the last group. This is exactly how grouped query attention works. In one group, all the keys matrices, all the value matrices will be the same. So the keys for head 1 will be the same for as keys for head 2 will be the same for keys for head 3 and keys for head 4. Values for head 1 will be the same as values for head 2 will be the same as values for head 3 will be the same as values for head 4. That's for one group. This will hold the same for all the groups, but between groups it will be different. For example, group 1 content will be completely different from group 2 content, will be completely different from group 3 content, etc. So I hope through this visualization you understood that latest state of the art models are also implementing the architectures which we are discussing in these lectures. It's just that it's very difficult to find such detailed explanations anywhere. People have written blog posts, but I find that such visualizations which I'm showing right now are very important for your understanding. And that's why I'm making these lectures a combination of whiteboard visualizations plus going in depth through the code. I don't want you to understand the code per se, but I plan to just show that you can download models from Hugging Face and you can explore these models further once you understand these concepts. So this is about grouped query attention. As a quick recap, in grouped query attention, what we do is that instead of all the heads sharing the same keys and values, we create groups. And within one group, we have the same values. So let's say group 1. In group 1, all the heads share the same keys. And in group 1, all the heads share the same values. In group 2, all the heads share the same keys. In group 2, all the heads share the same values. That is similar for the keys matrix, values matrix, and also WK and WV. So the advantage of grouped query attention or multi-query attention is that we are not saying that all heads will share the same thing. We are creating groups. So in terms of capturing diversity, it's better. And then there is also a trade-off with respect to size. So if you compare grouped query attention versus multi-query attention, in grouped query attention, let's see this, right? This is a good table to compare. If you compare grouped query and multi-query attention, you will see that in grouped query attention, there are G heads which need to be cached, which are the number of groups. Whereas in multi-query attention, we just need to cache just nothing. We just need to cache one head. But here we have to cache one head for every group. So the memory size increases by a factor of G from multi-query attention to group query attention. That's the disadvantage of GQA over MQA. But the advantage is, of course, the performance of GQA is better than MQA. And if you compare all of these three models together, multi-head attention versus multi-query versus group query, you will see that in terms of performance, context understanding, multi-head attention performs the best and multi-query performs the worst. Similarly, in terms of KV cache size, multi-head attention has the largest KV cache size, MQA has the smallest, and grouped query lies somewhere in the middle. But if you the main conclusion of the lecture is that GQA tries to optimize both. So in terms of performance and in terms of memory, it lies in the middle between multi-query attention and multi-head attention. What DeepSeek did is that they tried to answer the golden question. The golden question is that can we create something else over here for which my KV cache size would also be low and my performance would also be very good? Can I create something like this? Essentially, I want performance to be as good as the multi-head attention and I want my KV cache to also be very small. So can I have the best of both worlds? And it looks like an impossible problem to solve, right? If you try to have a good performance, you will of course have to have more memory. And but they solved this problem by introducing a very beautiful trick, which is the multi-head latent attention. In the next lecture, we are finally going to start looking at multi-head latent attention in a lot of detail. And there is also a coding module which I have in which we'll try to implement the multi-head latent attention from scratch. I know we have been building up to this lecture for quite some time now, but finally we are at this stage where we have literally covered everything. We covered self attention, we covered causal attention, we covered multi head attention, we covered key value cache, we covered MQA, we covered GQA. The only thing which is now remaining is to finally tackle the key innovation in the DeepSeek architecture. That's the multi head latent attention. This is what we'll be seeing in the next lecture. As the lectures get more deep and technical, I encourage you to maintain detailed notes of what you are learning, so that you don't feel lost along the way. And until now, it was very important to explain all these concepts to you, because otherwise it will be very hard to understand latent attention. And the beauty of what DeepSeek did, they really got the best of both worlds. They reduced the memory requirements of the KV cache, and they also got a great performance out of this mechanism called multi-head latent attention, which we'll look at in the next lecture. So thanks everyone, and I look forward to seeing you in the next lecture.